Hey everybody in Calc BC. Today we're going to be learning about lesson 4.2 parametric equations and calculus. And this is going to cover the first three lessons from College Board's Unit 9. And it is going to be an extension of parametric equations, starting to look at derivatives, right? So this is where we take the idea of parametric equations, which we talked about last lesson, like one equation that's represented with two kind of sub-equations, one for x equals and one for y equals, and they both have the variable t that they're in terms of, right? And we're going to talk about how do we differentiate, find the second derivative, and find the arc length of parametric equations. And I have the College Board kind of topics kind of laid out down here so that we can look at this a little bit more in depth. And so we have for differentiating, so finding the first derivative, we're going to talk about dy dx, which you're familiar with as being called the first derivative, but we're going to talk about how you can find that using dy dt and dx dt, otherwise known as the first derivative of the x equals and the y equals equations, or the x of t and the y of t. So we'll get into that. Second derivative, same idea. We're going to be doing the second derivative, which you're familiar with this notation, d squared y over dx squared. But we can find that using d dt of dy dx, which we'll talk about, and what that really means. And then we're going to talk about arc length. Arc length is technically a new vocabulary term, I believe. But arc length is just a fancy way of saying, it's similar to perimeter or circumference of something, right? So instead of just finding a straight length like we do oftentimes with a perimeter of like a rectangle, when we talk about a circle, we are still measuring the length around the object, but we call it the circumference. And it's as if we could cut part of the circle and then stretch it out straight. What would the length of that line segment be? And we're going to do that same thing with any type of curve for parametric equations. So if we have some curve, how do we find the length of the arc? Or how do we find the length of that curve if we stretched it out straight? How long would it be? So that's what we're going to be studying as well. Okay, so that's the three topics we're going to discuss today with parametric equations. So I'm going to pause the recording and get out the notes. All right, so here are our notes for 4.2 parametric equations and calculus. And right up here at the top, this is some really important definitions and equations or formulas that we're going to be using in this note. So let's take a look. If a smooth curve C is given by the equations x equals f of t and y equals g of t. So in other words, we have our x equals and our y equals on the right side is in terms of t. So it's a parametric equation. Then the slope of C at the point x comma y is given by dy dx equals dy dt over dx dt, where dx dt is not equal to 0. Okay, so let's break that down. Dx dt is not equal to 0. That makes sense, at least algebraically, because we are dividing by dx dt, so dx dt can't be 0, or we would be dividing by 0. I also think it makes sense that just looking at this function right here, or this equation, dy dx equals, we have dy dt over dx dt. So if you think about that algebraically, if you have dy dt over dx dt, remember, instead of dividing by a fraction, you can multiply by its reciprocal, right? So this is really dy dt times the reciprocal of the denominator, which is dt dx, which if we actually think of dy, dx, and dt as separate variables, the dt's are now canceling. So we end up with dy over dx. So algebraically it makes sense that this fraction would simplify to dy dx. But what's actually happening here, or how we're applying this, is saying we're going to be able to find a derivative that has a variable t in it, but it's going to represent the slope at the point, just like any normal xy plane equation would have a derivative, right? So if we have a curve, and let's say this with an arrow like this is our parametric equation with our x and our y, then right here if we could figure out what's the t, so what's the essentially the time when our particle exists right here, we could plug into some dy dx equation, that t variable, and get the slope of this tangent line, right? The slope, the xy slope, the normal slope that we're used to seeing. So we're not talking about speed, velocity, acceleration. Even though we're talking about particle motion here in this lesson, we're going to be talking about if this curve that's defined by this parametric equation is thought of just as a curve on an xy plane. If I could plug in a time, what's the slope of the tangent line up to that curve as a curve, right? We're not talking about motion right now, just the curve as it exists on the xy plane. So that's what we're going to be working with. So let's take a look at example 1 and see if we can apply this. And then we're going to move into second derivative then when we get there. Sorry, I just had to rearrange something on my computer. Okay, let's take a look at example 1. Given the parametric equations, x equals t squared plus 9 and y equals 4t to the 5th minus 6t cubed plus 3, find dy dx, and then we're going to come back and find the second derivative as well. So first, let's just think about that we know, we're just told that y equals 4t to the 5th minus 6t cubed plus 3. So if we wanted to define dy dt, remember what that notation means. It means that we're taking the derivative of y in terms of t. So we're going to do this the normal way that we find a derivative. It's going to be 20t to the 4th minus 18t squared plus 0. Okay, so that's our dy dt. If we have x equals t squared plus 9 and we're going to find dx dt, we would do that the same way, right? So this is just going to be 2t. So that was just kind of our normal derivative rules. Now let's apply this in context to find dy dx. So we found dy dt and dx dt. If we wanted to find dy dx, we were told at the top that that means we do dy dt over dx dt. And I think it's really important that when we're working with parametric equations and we do derivatives, we always want to use this notation, not just like y prime or x prime, because we want to know what we're doing the derivative in terms of, right? Because we're now going to be finding dy dx, whereas before we had dy dt. It's going to get really confusing if you just use the prime notation. So keep that in mind. I also want to make sure we know what this is really referring to, right? Dy dt, this is kind of thinking about the derivative of only the y motion of this parametric equation, and this is derivative of only the x motion. So it's kind of like we had two different viewpoints where we're just looking kind of like at a straight line motion from the x-axis and straight line motion from the y-axis, and now we're going to connect them to make dy dx. Anyway, let's just try this. So we already found dy dt was 20t to the 4th minus 18t squared, and dx dt was 2t. And lucky for us, we've got two terms on top but only one term on the bottom, so we can divide both of these top terms by 2t, and we would get 10t cubed minus 9t. So that is the dy dx. That's the first derivative. And that is pretty cool, again, because think about it like this. If this curve right here represents our parametric equation on the xy plane, we can just plug in t. We don't have to plug in the x or the y value of this point. But whatever the t is, remember t is kind of like the time that we get to this point. But if we plug in the t, we're going to get the slope of the curve at that point. All right. The second derivative is given by this, and this looks a little bit confusing at first, but it will make sense. So second derivative, remember the notation, it's d squared y over dx squared. And really what we're trying to do is take the derivative of the first derivative, right? That's normal. But right now, remember that our first derivative has a t variable in it. So how are we supposed to derive this in terms of x? It's kind of hard to do that, right? Because there's no x in here. We'd have to use implicit differentiation. It would have like a dt dx at the end of every one of these terms or something like that. So that would be a little tricky, right? We can't derive this in terms of x very easily. But here's what we can do instead. If we take the derivative of dy dx in terms of t, and then divide by dx dt, we've got that dt, and then we're eliminating the dt again, just like we did in this fraction situation right here. So that's what we're going to try to do. I'll show you. So first thing we need is we need the derivative of dy dx in terms of t. So we're going to take this first derivative, dy dx, that we found, and derive it in terms of t, which is, you know, the way that you would expect to derive this using the variable t. So we'd have, what, 30t squared minus 9. Okay, so now we have the ddt of dy dx, so the first derivative of dy dx in terms of t. And so then we're going to do the second derivative of this whole situation, which is going to be that 30t squared minus 9, right, over dx dt, and that's how we eliminate the dt and get back in terms of dx. So we've got to get this dx dt from over here and put it under here. And if we simplify this, we're going to end up with, what, 15t minus, and this part doesn't reduce, so it's just 9 over 2t. Or you could do 9/2 t to the negative 1. But that's our second derivative. Right? And again, it's not as simple as just taking the derivative of this, because this variable t isn't actually on our xy plane, right? It's kind of working in the background behind the scenes. So we need to kind of think twice about how we find the second derivative, but that's how you do it. All right? So first derivative is the derivative of y over the derivative of x in terms of t's. The second derivative is the derivative of the first derivative in terms of t divided by dx dt. Okay? Okay, we're going to practice this again. All right, example 2. Given the parametric equations x equals 5 sine of t and y equals 3 cosine of t, write an equation of the tangent line to the curve at the point where t equals 2 pi over 3. Okay, so remember, we're talking about where t equals 2 pi over 3. That doesn't necessarily automatically give us an x or a y value. So we don't even know the point on the curve where we're talking about yet. We have to be able to plug in t to find that. But we are going to want dy dt and dx dt. So let's just start with that. So I'm going to do the same thing we did up in example 1. So if we have y equals 3 cosine of t, the dy dt is going to be negative 3 sine of t. And then if we have x equals 5 sine of t, the dx dt is going to be 5 cosine of t. Okay. All right, so then we are going to want to have the first derivative, the dy dx. So remember, dy dx is going to be dy dt over dx dt, or in other words, what is it, negative 3 sine of t over 5 cosine of t, which you could also write as negative 3 fifths. And remember, sine divided by cosine is tangent. This is just negative 3 fifths tangent t. Okay, so now we have, all in terms of t, we have an x equation, a y equation, and a dy dx. So now what we need to do is find the point and the slope at this tangent line. And to do that, we're going to plug 2 pi over 3 into all of these equations. So we have to figure out x, we have to figure out y, and we have to figure out dy dx, all when t is 2 pi over 3. So we've got x equals 5 sine of 2 pi over 3, which is 5 times root 3 over 2. That's going to test your memory of your unit circle. So we've got 5 root 3 over 2. For the y, we've got negative 3 times the sine of 2 pi over 3 again. Sine of, what am I doing? I plugged that into dy dt. Undo, 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 undo. It's 3 times the cosine of 2 pi over 3. And let's see. So we've got 3 times negative 1/2. So this one's negative 3/2. And then for dy dx, we figured that out up here. So it's going to be negative 3/5 times the tangent of 2 pi over 3. Again, with that same t value that we were given in the initial question. This is going to be negative 3/5 times negative root 3. So we're going to get negative times a negative. So it's positive 3 root 3 over 5. Okay, so I'm just going to plug this into point slope form. So we have y minus y1 equals m times x minus x1. And so our y was negative 3/2. And so that's going to be y plus 3/2 equals the slope, which is 3 root 3 over 5 times x minus 5 root 3 over 2. And that's a valid answer. I don't have to solve that for y, but I could pretty easily. And just to review, if we sketched this curve with the x equals and the y equals that are given, then at the point 5 root 3 over 2, comma, negative 3/2, this curve would go through that point, and it would have a slope of 3 root 3 over 5 at that point. And this is the equation of the tangent line to the curve at that point. All right, so that's what we got. Let's look at example 3. Find all points of horizontal and vertical tangency given these parametric equations. Okay, so remember, we're going to be looking at the tangent lines here. To find horizontal tangency, it's going to mean that the slope or the derivative equals 0, right? Because that's what causes a horizontal line to be the tangent line. And if the tangent line or the derivative doesn't exist, if the derivative doesn't exist, it means it has a vertical tangent line, right? So that's what we're going to be looking for here. So let's try this. So first of all, we're going to have to find an equation for dy dx. So dx dt is going to be what? 6t minus 6, and dy dt is going to be what? 2t minus 8. So then dy dx is going to be dy dt over dx dt. So that'll be 2t minus 8 over 6t minus 6. And that's not easily simplified, so I'm just going to leave it that way. So let's kind of explore that tangent line equation, or rather the first derivative. So for horizontal, if we have horizontal tangency, it means that dy dx is going to be 0, right? So how do we make this equation equal 0? Well, the numerator has to equal 0 for the fraction to equal 0, right? Because 0 over anything equals 0. If I divide by 0, I don't necessarily equal 0. I definitely don't equal 0. So we want to set the numerator equal to 0 and solve for t. So t is 4. Okay, so when t is 4, we must have a horizontal tangent line. And that doesn't answer the question, though. It wants to know the points with the horizontal and vertical tangency. So we know t is 4. We got to plug that back into the original for x and y to find the actual ordered pair where this is happening. So for x, we're going to plug in 4 for t. So that's going to be 24. And for y, we're going to plug in 4 for t. and that's going to be -7. So the point with the horizontal tangency has an ordered pair of 24, -7. Okay, we're going to do the same thing for the vertical tangent line, and vertical tangent lines are going to happen when dy dx does not exist. Okay, we're going to check that, and then we're going to check the to make sure there's actually a point there and it's not some other issue why the first derivative might not exist. But if we have a polynomial or a rational expression here that's representing our first derivative, we know that this fraction won't exist if the denominator equals 0. So we're going to set the denominator equal to 0 this time. And t equals 1. So now we're going to plug in 1 for every t in the x and the y's to figure out the ordered pair this time. So we've got 3 times 1 squared minus 6 times 1, or -3, and 1 squared minus 8 times 1 plus 9, or 2. So we've got -3 comma 2. So that point is going to have a vertical tangent line. Okay, so that is example 3. All right, I wanted to show you what this looks like on a calculator graphically real quick. So I went to my calculator, I went to mode, and I changed to parametric mode so that I could type in an x and a y equals in terms of t. And I plugged this straight in from the beginning of the question so we could look at the graph. Remember, the graph is graphing both of these simultaneously by checking at every t value what the x and the y are, and then plotting the x and the y points. The t points, the t values don't get graphed on the graph itself. But if I take a look at the graph here, I already changed my viewing window a little bit to fit the curve. You can see that we were supposed to have a vertical tangent line at -3 comma 2, and you can see at -3, 2, we've got a vertical looking tangent line there, right there at that point. And then at 24, -7, which is right about over here, you can tell that this curve, you can't see it going back up, but that's what it's doing. We've got a horizontal tangent line right there that we found algebraically. All right, so that's the graph that shows exactly what's going on here and how we successfully found the points of horizontal and vertical tangency. Now we are ready for example 4. All right, here's the last new formula in this lesson, which is for arc length. And remember, I said at the beginning of the lesson that arc length is similar to the idea of circumference. So the circumference of a circle says, what if we take this circle, cut a part of it, and then stretch it out straight? How long would that straight line segment be? Now curve that up. That's the length of the the curve in the circle. Circumference is another name for the arc length of an entire circle. An arc length for a parametric graph, so for any curve, so let's say from here to here, if we stretch that out straight, we will want to know how long is it. And basically what this formula right here does is it takes points, that are close together, and then uses the Pythagorean theorem to say, hey, what would the length of the hypotenuse between these 2 points be? Or the distance formula even, you could say. And so it finds the distance between points that are closer and closer together, kind of like an integral does, and adds them all up until we get the length of the curve. We're going to be studying arc length a lot more in a future unit, but for now, this is the formula that we need to know. So the arc length for a parametric graph is s equals the integral from a to b. A and b are t values. And then we have this kind of distance formula looking thing in here. So the formula works when the curve does not intersect itself and the curve must be smooth. So we can't have any corners or holes. Okay. Set up the integral expression for the arc length of the curve given by the parametric equations. X equals e to the 5t plus 2 and y equals 3 sine of t squared. We're going to find the length of the arc from t equals 0 to t equals 4, and do not evaluate. So you can tell based off of this equation, we're going to need dx dt and dy dt. So let's find that first. Okay, so we need to Find the derivative of e to the 5t plus 2, which hopefully you can see is going to be e to the 5t plus 2 times the derivative of the exponent, which is just 5. So we could write that as 5e to the 5t plus 2. And if we find dy dt, what's going to happen here? So the derivative of sine is cosine, so it's going to be 3 cosine of t squared times the derivative of the inside, which is 2t. So I'm going to rewrite that as 6t cosine of t squared. Okay? And that's all we need. So now we can go to our integral. We know we're going from 0 to 4. So s equals the integral from 0 to 4 of the square root of dx dt squared plus dy dt squared dt. Okay? So all we had to do was set that integral up. We don't have to solve it or evaluate it, but we did that correctly. And if we wanted to, we could go to our graph just to make sure that this curve does not intersect itself, but I'll tell you right now that it doesn't, so we can save a little bit of time in this video. But that's what we're doing, okay? Again, we're gonna come back to arc length later on. We're gonna study arc length for, like regular curves that are defined as y equals instead of with t's. But that's all you need to know for now, okay? So again, the 3 things we learned in this lesson were how to find the first derivative and the second derivative of a parametric, and how to find the arc length of a parametric curve. All right, so I hope that makes sense. Let me know if you have any questions. Good luck with the worksheet, and I hope you have a great day. Thank you very much for watching.